Hello, good morning, students. Welcome back. So, today we are going to discuss our new chapter is structure of atom. Okay, so atoms are the fundamental particles. Okay, they are the fundamental building blocks of matter. The existence of atom has been proposed by scientists during early ages. So, the during early ages, the atom was discovered. Okay, so they said that atoms are non-divisible. What do you mean by non-divisible? That they cannot be further divided. Okay, so based on that, in 1808 there was a scientist called Dalton. Okay, Dalton, what he did, he proposed Dalton's atomic theory. And he said that atom has a ultimate particle of matter. So it is said to be a ultimate particle of matter according to his Dalton's atomic theory. Then what happened? Like, as the scientists started discovering, uh, there were many studies going on about the atom. So then towards the end of the 19th century and towards the somewhere near the starting of the 20th century, some of the scientists who discovered that atoms can be further subdivided. Okay, they can be further subdivided into subatomic particles. And which are the subatomic particles? They are nothing but electron, proton, and neutron. So we'll be discussing about the fundamental particles. Okay, so these are some of the fundamental particles of atom. So the first one is Okay, so the first one is electron. So the first fundamental particle is electron. So this electron was discovered by J.J. Thomson. Okay, J.J. Thomson, he discovered electron. So these electrons are negatively charged particles. Electron is negatively charged particle. What is the charge? So charge is minus 1.60 into 10 raised to minus 19 coulombs. Okay. And what is the mass of the electron? It is 9.1 into 10 raised to minus 31 kg. It is 9.1 into 10 raised to minus 31 kg. What is proton? Okay, the second fundamental particle was proton. So this proton was discovered by Goldstein. Okay, so remember who discovered which fundamental particle? Important asked. Okay, it is asked. So proton, it was discovered by Goldstein. So it is a positively charged particle, and the charge is what? It is plus 1.602. Okay, into 10 raised to minus 19 coulombs. And what is the mass? It is 1.673 into 10 raised to minus 27 kg. Okay, into 10 raised to minus 27 kg. Then the next fundamental particle was neutron. So who discovered neutron? Neutron was discovered by Chadwick. Okay, so it is a neutral particle. Neutral particle means what? It is zero. Okay, it is neither positive, neither negative. It is having zero charge. So what is the charge? So the charge is zero. And what is the mass? Mass is 1.675 into 10 raised to minus 27 kg. So these are some of the fundamental particles of atom. Okay, remember who discovered, remember the scientist name, remember the charge and the mass. Okay, so this is about the fundamental particles. So next, so alpha rays. Okay, you know alpha rays. So these alpha rays also have some mass. Okay, so what is the mass of alpha rays? It is 6.67 into 10 raised to minus 27 kg. Okay, it is 6.67 into 10 raised to minus 27 kg. And what is the charge? The charge is plus 2. Okay, the charge of alpha rays is plus 2. And these alpha rays are nothing but they are the helium nuclei. Okay, so they are the helium nuclei. So based on this, we'll solve a question. So the lightest particle is, okay. So how do you understand which is the lightest particle? By considering its mass, okay, by considering its mass. So we'll see mass of each of the, so the option is first is what? It is electron, okay. So electron, what is the mass of the electron? So what is the mass of the electron? It was 9.1 into 10 raised to minus 31 kg. Okay. So this is the mass of the electron. So what is the mass of the proton? So proton, the mass was given as 1.673 into 10 raised to minus 27 kg. Okay. Then what is the mass of neutron? So it is 1.675 into 10 raised to minus 27 kg. Okay. And what is the mass of alpha particle? It was 6.67 into 10 raised to minus 27 kg. Okay. So when you see the negative scale, so negative, so all are minus 27. So minus 27 is greatest or minus 31. So which is this lightest particle? Minus 31. Okay, minus 31, it comes first. So the lightest particle is electron. Okay, electron is the lightest particle. Minus 31 is a smaller unit than minus 27. So this is the correct answer. So next. Alpha particles are, just a second. So alpha particles are represented by, okay. So A, helium atom, B, helium nuclei, C, hydrogen nuclei, D, hydrogen atom. Which, how is alpha particles represented as? B, yes, it is helium nuclei. Correct answer is helium nuclei. So the next question is, neutron is discovered by. So who discovered neutron? We saw the chart, right? So various particles, who discovered? Yes, Chadwick. Okay, he discovered A. Option A is the correct answer. Okay, so neutron was discovered by Chadwick. So next. So before going to this, we'll first see what is atomic number. Okay, what is atomic number? Atomic number is nothing but it is the number of protons in the nucleus of an atom. It tells you about the number of protons, okay, they are which are present in the nucleus, or it tells you the number of electrons which are present in a neutral atom. Okay, so how the element is represented, you can see here. Okay, how the element is represented. So X. So X is the any element. The Z. Okay. Z is nothing but your atomic number. A is your mass number. Okay. So for example, now this is the example, calcium. Calcium is a element. So what is its atomic number? Atomic number is 20. What is its mass number? It is 40. Okay. So this represents your mass number. 20 represents your atomic number. So what is atomic number? Number of protons in the nucleus, or other definition is number of electrons in a neutral atom. So how many new protons are present in calcium? So it is 20. Okay, 20 protons are present. So it is 20 protons are present. Okay, and how many electrons are present? Electrons are also 20. Okay, 20 electrons are present. Then protons and neutrons. Protons and neutrons together, they are called as what? Nucleons. Remember this. Okay, protons and neutrons together, they are called as nucleons. Then what is mass number? Okay, what is mass number? Mass number is represented by what? It is represented by A. So mass number is given as number of protons plus number of neutrons. Okay, mass number is given as number of protons and number of neutrons. So from this example, okay, this calcium examples, calculate the this. Now we know what is the mass number. Mass number is 40. Okay, what is proton? This. Yes, just a second. So what is the number of protons? Number of protons is this. Okay, what is the atomic number? It is 20. And you have to find what are the number of neutrons. So you keep it aside. So 40, shift this 20 this side. So how many are the neutrons? They are 20. So 20 neutrons. So remember this, atomic number is nothing but number of protons as well as number of electrons. What is nucleons? Nucleons is protons and neutrons together. They are called as nucleons. And what is mass number? How do you calculate mass number? Number of protons plus number of neutrons. Okay, so now we'll see some of the different types of atomic species. Okay, we'll see about the atomic species. So isotopes. What are isotopes? Isotopes are nothing but they have same atomic number and different mass number, but their mass is different. Okay, so they have same atomic number but different mass number, and they have same properties. They have same chemical properties. For example, these are the isotopes of hydrogen. You can see these are the isotopes of hydrogen. Okay, these are the isotopes of hydrogen. So this, you can see the atomic number. What is the atomic number? 1, right? They are having same atomic number, and you can see the mass number are varying. So it is 1, 2, and 3. When the proton, so this is a proton. Okay, it is protium. This is deuterium. Okay, this is deuterium and this is tritium. So which is the radioactive isotopes of hydrogen? It is tritium. Remember this, tritium is the radioactive element. Okay, it is a radioactive element or a radioactive isotope of hydrogen. So these are the isotopes. Okay, isotopes of hydrogen. Now second example, you can see these are the isotopes of oxygen. What you can see, oxygen, they are having same atomic number. What is atomic number? It is 8. And you can see the mass number are varying, right? So these are the 3 isotopes of oxygen. Second, next is isobars. Okay, remember this definition. They may ask you with an example, and they'll ask you which is the example of isotope, or they'll give you options. Then you have to tell whether it is isotopes, isobars, like that. Okay, then next is isobars. What do you mean by isobars? When you have same mass number but different atomic number. Okay, so when you have same mass number but different atomic number, then it is said to be isobars. So see example. So argon, okay, Ar40. You can see the mass number are 40 in each case. Okay, potassium is 40, calcium is 40. So these are having same mass number. You can see the atomic number. Okay, 18, 19, 20. So they have different atomic number. So when you have same atomic number, when you have same mass number but different atomic number, they are said to be isobars. Okay, remember this. Next, isotones. Okay, what are isotones? Isotones are nothing but they are having same number of neutrons. Okay, same number of neutrons are present. How do you calculate neutrons now? How do you calculate neutrons? Mass number is equals to what? Number of protons plus number of neutrons. Okay, so you know in this case the masses are given, right? So you put the for silicon, what is the mass number is 30. Proton is how many? 14. Okay, so how much you are getting? Just see in each case, right? So you solve for the each year, how much it will be? So 16, right? It is, so shift here 13 minus 14 gives you 16 neutrons. Okay, neutrons are 16. Then with phosphorus, phosphorus. So in all these three cases, the number of neutrons are same. Okay, the number of neutrons are same for different atomic number. You can see the atomic number is changing, right? But they are having same number of neutrons. So remember, what are isotones? They are having same number of neutrons for different atomic number. Okay, so we'll go to the next. What are isoelectric species? So in the last class also I discussed about isoelectronic species or isoelectric species. What do you mean by isoelectric species? Isoelectronic species is what? They are having same number of electrons. Okay, they are having same number of electrons. Same number of electrons. See, we'll see what is same number of electrons. How do you calculate electrons? How do you calculate electrons? When you have atomic number, right? What is atomic number? Is nothing but number of protons or number of electrons. So you know the atomic number of each. Now here, what is the atomic number of nitrogen? Is 7, oxygen is 8, then carbon is 6. So we'll solve here. So nitrogen, how many nitrogen? 2 nitrogens are there into 7 plus oxygen is how much? Oxygen is 8. See how much it is? How many electrons? 22 electrons, right? Then for CO2, how many? Carbon is 1, 6 plus oxygen is 8, 8 into 2. So this is also 22 electrons. Then for CNO minus, okay, carbon is 6, nitrogen is 7, oxygen is 8, minus. Whenever you have minus means what? You have to add 1 electron. Whenever you have plus, you have to remove 1 electron. So in this case, you have to add. So remember, whenever you have negative charge, you have to, what you have to do? You have to add 1 electron. So how much it will? It will come to 22 electrons. So what is isoelectronic species? Isoelectronic species is nothing but they are having same number of electrons. Okay. So a question, atoms with same mass number but different atomic numbers are called, what they are called? Yes, what they are called? What they are called? They are called as isobars, correct. Okay, they are called as isobars. Then the number of neutrons in di-positive zinc ion with mass number 70 is, okay, what is given? What is given? It is, we have to calculate what? We have to calculate number of neutrons. For which element? It is di-positive. Di-positive means what? It will have, zinc will have +2 charge. Okay. So what is its mass number? Mass number is 70. How do you calculate neutrons? Neutrons, how you calculate? Mass number equals to number of protons plus number of neutrons, right? So we know mass number is 70. We know this protons is what? The atomic number. What is the atomic number of zinc? It is 30. So it is 30. Okay, 30. Then we don't know what is neutron. So 70 minus 30 gives you what? It will give you 40, right? But okay, so this is with respect to di-positive. But what you can see here, this is for zinc. Okay, this is for zinc, number of neutrons for zinc. But it is what? It is +2, right? It is +2. +2 means what I said? +2 means you have to remove electrons, remove neutrons. Okay, so when you remove this this, it will be 38. So the correct answer is C. So we'll go to the next. What are nucleons? Yes, what are nucleons? What are nucleons? What are nucleons? What is a nucleons are B. Yes, neutrons and protons together are called as nucleons. Okay. So next we'll see the atomic models. Okay, atomic models. So atomic models, these were proposed. Okay, these were proposed to explain the distribution. Okay, the distributions of the charged particle in an atom. So these atomic models. So there were mainly two models were proposed. So one model was proposed by Sir J.J. Thomson. Okay, Thomson. So J.J. Thomson, he gave one model, and second model was proposed by Rutherford. Okay, so we'll see. So why they were proposed? To see the uniform distribution or to see the stability of an atom. So atomic models. Okay, atomic models. So this Thomson model. So first is our Thomson model. So this Thomson model was given by J.J. Thomson in the year 1898. Okay, it was given in the year 1898. So this model, how it is visualized, you can see this diagram, right? You can see this picture. So you can see the red color. Okay, the red color, it is nothing but, so what he said, that atom, okay, this atom, it looks like a spherical shape. So atom has a spherical shape with which the positive charge is uniformly distributed and the electrons are embedded in such a way to give a stable electrostatic arrangement. Okay, this was a statement given by Thomson. Now, what do you mean by this? You can see this picture. Okay, you can see the red part. Okay, this red part is nothing but it is said to be a positive charge. Okay, which is distributed all over. Okay, all over. So consider that to be an atom. So atom, which is a spherical shape, and this positive charge is uniformly distributed. And the round, okay, the white color, whatever the round, this are there. So these are nothing but electrons. And these electrons, what he said, they are embedded. Okay, they are embedded, or they are they are embedded in such a way to give a stable electrostatic attraction arrangement. Now, what do you mean by electrostatic arrangement? Electrostatic is nothing but it is a force of attraction between and this. Okay, and now plus and negative. So whenever you have like charges, what it will do, it will repel. Okay, and whenever you have unlike charges, they will attract. Now positive charge, okay, this positive charge is nothing but protons. So protons are distributed uniformly and the electrons are embedded. Electrons is what? It is negative charge. So the electrons are placed in such a way that they are having electrostatic arrangement, that is there is some force between there. Okay, there is some attraction between them. So this model, it explained the neutrality of the atom. Neutrality of the atom was explained by this model, but he could not explain the result of scattering experiment. Scattering experiment was given by Rutherford. Okay, so this model, it explained the overall neutrality. How the overall neutrality? Because there was positive charge and negative charge. So when positive and negative charges are present in an equal proportion, so there will be overall, the overall surface will be a neutral. So this explained the overall neutrality of the atom. So this Thomson model, it looks like plum pudding model. Okay, it is called as plum pudding model, or it looks like a watermelon model. Okay, watermelon. So you know watermelon. So when you cut the watermelon into two half, so the one half, if you take, you can see at the surface, okay, the red, the fruit, the which is in red color. So that is nothing but it is said to be a positive charge. That is, a positive charge is uniformly distributed, and the seeds of the watermelon, they are nothing but they are the electrons. Okay, so Thomson, he compared this model with the watermelon model, or with the plum pudding model. So this was Thomson model. So next is Rutherford's nuclear model of atom. So what nuclear Rutherford gave, or what was his model? Okay, what his model explained. So an atom consists of small positively charged nuclei and electrons revolve around it. Okay, so So what was his experiment? You can see this setup. Okay, this was his experiment. This was a source. Okay, this was a source from which the electron beams. Okay, this was a, just a second. So this was a source from which the alpha particles were made to struck on this gold foil. So he took a source from which the alpha particles were bombarded. This was a gold foil, and around it there was a circular photographic plate which was made of ZNS, okay, zinc sulfide. So this was a photoelectric plate. So what he did, he bombarded the alpha particles on this gold foil. So after bombarding the gold particles, he could see some observations. What was the observation? Some of the alpha particles, most of the alpha particles, they went through this. Okay, it went through this gold foil. Okay, then only few. Okay, then some of the alpha particles, what happened? It got deviated. Okay, it got reflected by some angle. You can see this. I'm just giving in the other colors. I'm just drawing them in other colors. So most of the alpha particles, they got transferred, or it went through the plate. Some of the this, okay, particles, they got deviated. Then other alpha particle, only few, okay, only few alpha particles, when they were bombarded on the gold foil, they went bounced back with what? It went back. Okay, so from this, what he concluded, what he gave conclusion, that most of the space around the atom may be empty. Okay, may be empty, and the nucleus will be having, or the nucleus or the positive charge is somewhere in embedded in a small place. Okay, it is not all over, but the nucleus is present in a very small place. Okay, so this was put forth by Rutherford. So only few deflected back. So extremely small region, the nucleus was placed, and the charge was surrounding around it. Okay. Then what was the next point was that nucleus. Okay, this nucleus is surrounded by electrons. The nucleus may be surrounded by electrons, and they move around the nucleus in a very high speed. Okay, and in a circular orbits. They were moving in a circular orbits. Then this electrons and neutrons, they were held by a very strong force of attraction, and they are nothing but electrostatic force of attraction. So so this was Rutherford's nuclear model of atom. So he said that there is a positively charged nuclei which is embedded in a very small place. It is not entirely uniformly distributed, but it is somewhere in a small size. Okay, it is somewhere in the center, and the electrons are revolving around them. So, and they are held with a strong force of attraction, electrostatic force of attraction. So this was nuclear model of atom. So these were mainly the two important models. Then, but these two important models, they could not explain the stability of atom. They could not explain the line spectra of elements. What are line spectra? Line spectra is nothing but whenever the elements are bombarded with some radioactive element, okay, they will give they will emit some radiation, and they, when you put it into the spectrometer, okay, they will give you a graph like sheet. So the elements will show some spectras. So this is nothing but line spectra of elements, and they fail to give the distribution of electrons and energies of electron. So these two models, they failed to this contribution. So we'll solve some of the problems. So which of the following conclusions could not be derived from Rutherford's alpha particle scattering experiment? So which was the conclusion he could not derive? So most of the space in the atom was empty. He said that. Okay. And the radius of atom is 10 raised to minus 10, while that of the nucleus is 10 raised to minus 15. Okay. So I said, so the radius is larger and nucleus is embedded somewhere in the center. So the radius is very small. So this is also correct. Then the third point, electrons move in a circular path of fixed energy called orbits. No, right? So this was not included in his model. Okay. So electrons move in a circular path of fixed energy called orbit. So this was from Bohr's postulate. So this sentence is not from, or this is not derived from Rutherford's alpha particle scattering experiment. This was from Bohr's. So this is the conclusion. This is wrong. Okay, which this is wrong. Electrons and nucleus are held together. So these three statements were from Rutherford's alpha scattering experiment. This is wrong. This is from Bohr's. Okay. So next. Which of the following properties of atom could be explained correctly by Thomson? What did Thomson say, or what he explained from his model? Yes, these are the four options. These are the four options. Yes, which is the correct one? Overall neutrality of atom, right? So overall neutrality of atom was explained from Thomson's model. So now next is electromagnetic radiation. What do you mean by electromagnetic radiations? Okay, electromagnetic radiations means what? Radiations which have both electric as well as magnetic fields, and they travel in a wave. Okay, so both they are having both electric as well as magnetic field to travel in the form of wave. So these are nothing but electromagnetic radiations. Now these electromagnetic radiations, they are having dual character. What do you mean by dual character? What do you mean by dual character? Dual character means what? They have two properties. Okay, they may be having both wave-like as well as particle-like properties. Electromagnetic radiations, they may have two properties, dual nature. Okay, they are having two characters. One, it acts like a wave nature or wave-like, and second is it acts like a particle. Okay, it acts like a particle. Now, this wave nature of electromagnetic radiation, first we'll see what is the wave nature of electromagnetic radiation. So these charged particles, okay, charged particles under so this wave nature, it was given by James Maxwell. Okay, wave nature of electromagnetic radiation, it was explained by whom? It was explained by James Maxwell in the year, just a second. So it was explained by James Maxwell in the year 1870. Okay, so what he explained, that the charged particles move under acceleration with alternating electrical and magnetic fields which are produced and transmitted. Okay, so these are electrically charged as well as magnetically charged under acceleration to produce the electromagnetic waves. Okay, so these consist of both. Why they are, so they are having both electric as well as magnetic field, and these components are perpendicular to each other, or these electric and magnetic field, they are perpendicular to the direction with which the wave is propagating. Okay, how the wave is moving in that direction, this electric and magnetic fields, they are placing perpendicular to each other. Okay, and what are the characteristics of wave? So there are few characteristics of wave. How do you represent a wave? So there are, which are the characteristics of wave? So wavelength, right? How do you, so these are the four characteristics of wave. So first is wavelength, second frequency, wave number, and velocity. What do you mean by wavelength? Okay, wavelength is nothing but it is the distance between the two consecutive crust and trough. Okay, just a second. So it is a distance between the, it is a distance between the two crust and troughs. So when you write, so when you draw a wave, okay, this is a wave. So this is a crest, this is a trough. So this distance is nothing but your wavelength. Okay, so the distance between the crest and between two consecutive crust and trough is called to be a wavelength. How it is denoted? It is denoted by lambda. And what is the SI unit? It is denoted by meters. Okay, M. Then next is frequency. What is frequency? Frequency is nothing but the number of waves which pass through a given point in a 1 second. Okay, in 1 second, how many waves pass? Okay, in a given point. Through a given point, it is said to be a frequency. Frequency is given as hertz and the SI unit is per second. It is given as hertz or per second. Okay, so this is frequency. What is frequency? Frequency is nothing but number of waves which travels through a given point in 1 second. What is wave number and how is frequency denoted? Mu. Okay, it is denoted by mu. What is wave number? Wave number is denoted by mu bar. Okay, so what is wave number? So number of wavelengths per length. Okay, per unit length. So number of wavelengths per unit length is nothing but your wave number. How it is related? You can see here wave number is nothing but it is inversely proportional to wavelength. So it is the number of wavelengths per unit length. So how it is? The SI unit is per meter. Okay, per meter. Wavelength is given in meter. So it is inversely proportional. So it will become per meter. Okay, velocity. Next is the next characteristic of a wave is velocity. What do you mean by velocity? It is denoted by small c. Okay, it is denoted by small c. And what is velocity? Velocity is nothing but the speed. Okay, velocity is nothing but the speed with which it travels. Now the speed of the light is nothing but c 3 into 10 raised to 8 meter per second. So c, okay, velocity with which it travels. So c is given as 3 into 10 raised to 8 meter per second. Now how is the relationship between lambda, c and mu? It is given by c is equals to mu into lambda. C is nothing but your velocity, mu is your frequency, lambda is your wavelength. So this is the relationship. Remember this. Based on this, questions are asked. Okay. Next. Sir, I'm not able to move. The slide is not getting front.
Can you close and open, ma'am?
Sir, close and open.
Yeah. You can present now, ma'am.
Yes. So next is electromagnetic spectrum. Okay, what do you mean by electromagnetic spectrum? So arranging the electromagnetic radiations. Okay, there are different radiations in order of the increasing wavelength or decreasing frequency. So when you are arranging the electromagnetic radiation in increasing wavelength, okay, or decreasing frequency, it is nothing but electromagnetic spectrum. It gives rise to electromagnetic spectrum. So these electromagnetic spectrum, so here you can see these are some of the radiations, okay, electromagnetic radiations. So they are arranged in the order of their increasing wavelength, okay, increasing wavelength. So cosmic rays, so these cosmic rays are nothing but what? They are the atom fragments that that comes down from the outside of the earth, okay, it comes from outside of the solar system on the earth. So these are the cosmic rays. So this cosmic rays, then these are gamma rays, then comes the x-rays, then uv rays, visible region, okay, then infrared rays, then microwaves and radio waves. So these are the radiations which are arranged in their increasing order of wavelength, okay. So this gives rise to a spectrum, electromagnetic spectrum. So next comes the particle nature of electromagnetic radiation. So we discussed about the wave nature. So this is the particle nature of electromagnetic radiation. So particle nature of electromagnetic radiations was given by Planck. So there was a Planck, Max Planck. So he gave his quantum theory. So what he said, according to his theory, that electromagnetic radiations are emitting discontinuously. Okay, the radiations are not continuous, but they are discontinuous. Okay, they are discontinuously in the form of small packets. Okay, so electromagnetic radiations are emitted discontinuously in the form of small packets of energy, and these small packets are called as photons, or they are called as quanta. Okay, so electromagnetic radiations which are emitted in the form of small packets of energy which are discontinuous are called as photons or quanta. So how this energy is given? So energy is equals to h nu. What is h? H is here the Planck's constant. Okay, Planck's constant. So what is Planck's constant? The value is 6.624 into 10 raised to minus 34 joule second. Okay, so this is Planck's constant. So h is the value, and what is mu? Mu is your frequency. Okay, it is a frequency. Now how do you relate this mu? Okay, you can you know, C is equals to mu into lambda. Okay, so mu, so what happens to mu? So this C by lambda. Okay, so by replacing this value of mu, you will get this as your equation. So energy of each photon is given as H is equals to C by lambda. Okay, so energy is equals to H nu. By adding the value of mu from this particular equation, you get this formula. Okay, so remember this. So here, what is H? H is nothing but Planck's constant. And what is its value? 6.624 into 10 raised to minus 34 joule second. So particle nature of electromagnetic radiation, it explains two important concepts. First is black body radiation. What do you mean by black body? Okay, a body which emits and absorbs all type of radiations, okay, is called as black body, and the radiations emitted by such a body is called as black body radiation. Okay, so what is black body? Black body radiation. See, black body radiation. What is black body radiation? It is the black body is nothing but it is the amount of energy it takes, all the, it emits and it absorbs all the types of energy. It absorbs and emits all the types of energy, and the radiation emitted by a black body is called as a black body radiation. Okay, the next concept is photoelectric effect. What is photoelectric effect? What is done? A metal surface is taken. Okay, metal surface is taken and a beam of light is taken. So what is done? A beam of light is made to strike on a metal surface. So when a beam of light is struck on a metal surface, immediately within the no time gap, there will be a emission of electrons from that surface of, okay. So this is nothing but photoelectric effect. This is called as photoelectric effect. What is done? A beam of light is being struck on a metal surface. So as soon as the metal surface is hit by the light, okay, beam of light, there will be emission of electrons. So this is nothing but your photoelectric effect. Now this photoelectric effect, the kinetic energy of this photoelectric effect can be calculated as, you know, what is kinetic energy? Kinetic energy is nothing but is your half mv square. So kinetic energy is given as half mv square. So this half mv square h nu, okay, you know what is kinetic energy? Energy, okay, energy is equals to h nu, right? Energy is equals to h nu. So this change in energy, okay, is given by h nu minus h mu naught. So this mu naught is nothing but it is the frequency required to eject electron. As soon as the metal is hit with the light, so there will be ejection of electrons. That is a change in frequency, that is mu naught. Okay, so this mu naught is nothing but it is called as a threshold frequency. It is a minimum energy, or it is a minimum frequency. Okay, so this is mu naught. So this is the kinetic energy. It can be calculated. Okay, so this is photoelectric effect. So we'll solve some of the problem based on electromagnetic radiations. Suppose 10 raised to minus 17 joules of energy is needed by the interior of human eye to see an object. How many photons of green light, that is lambda is 550 nanometer, are needed this minimum amount of energy? Now what is given here? Okay, here okay, so you know what is energy? Energy is equals to h nu, right? The energy is given as h nu. Now what is the energy given? Energy is, what are the given quantities? E is equals to 10 raised to minus 17 joule. Now what is the lambda? What all are given? You have to write first. So lambda is wavelength, right? Wavelength is given as 550 nanometer. Now what we have to find? Okay, now we have to find how many photons, okay, how many photons of green light are needed for this minimum amount of energy. So how to solve this? Okay, E is equals to h nu. We have to find the number of photons. So you have to take E is equals to n h nu. Okay, you have to find the number of photons, n. So now E is equals to, so what is given? Wavelength is given. So you have to replace this by C is equals to, you know, mu lambda. So mu is equals to C by lambda. So write this, n is equals to n into h by c lambda. Okay, so this will give you what? Substitute, you know, the values. Now here what we know is here energy. We know energy is what? 10 raised to minus 17, right, joules. N we have to find out. H is what? Planck's constant. It is 6.624 into 10 raised to minus 34. Then what is C? C also we know. It is 3 into 10 raised to 8. Okay, meter per second. What is lambda? Lambda is 550. So we have to convert it into nanometer. So it will be 550 into 10 raised to minus 9. Okay, so after this, what you have to find? N. So what you do? Just take it that other side. So n is equals to, okay, n is equals to, what will happen? N is equals to 10. This will go that side. So it will be 10 raised to minus 17 into 550 into 10 raised to minus 9 divided by 6.624 into 10 raised to minus 34. Okay, 34 into 10 raised to 3 into 10 raised to 8. Okay, so now solve this. and see what answer you get. Solve this.
Question is not changing, ma'am. Slide is not changing. You are on the 22nd slide.
22nd slide, sir.
Which question you are solving, ma'am?
So just a second.
Okay.
Same problem.
You are on the mute, ma'am.
So, so is it visible? Suppose 10 raised to minus 17 joules.
Yes, ma'am. Correct, ma'am.
Yeah, okay. So before this, so here you can see it was stuck on here, I guess, sir. So this was a formula. Okay, we are going to use E is equals to H2. So here mu can be replaced by, okay, mu. Okay, so H E is equals to H mu. So this mu C is equals to C is equals to mu is equals to C into lambda. Okay, so it gives you a value. So based on this particular formula, you're going to solve this. It's getting stuck. So here, so what are the entities given? Okay, energy is given. You can see, suppose 10 raised to 17 joules of energy is needed by the interior of human eye to see an object. How many protons of green light, okay, that is lambda is equals to 550 nanometer, are needed, this minimum amount of energy. So what is given? Given is energy. Energy is equals to 10 raised to minus 17 joules. Okay. Then what else is given? Lambda. Lambda is given as 550 nanometer. So by what we have to find out is how many protons of green light are needed for this minimum amount of energy. So by using the Planck's E is equals to N is equals to H mu. Okay, N is what we are going to find out the number of photons. Okay, so energy is what? Energy is given as 10 raised to minus 17. Okay, then N we have to find out. What is H? H is nothing but your Planck's constant. It is 6.6. Okay, it is 6.624 into 10 raised to minus 34. Then mu. What is given? Mu, we don't know. They have given in terms of lambda. So the relationship between this is what? C is equals to mu into lambda. We know this. So by substituting this, what we get? We get C into lambda. Okay, so here E is equals to NHC by lambda. So now what is the value of C? C is 3 into 10 raised to 8. Okay, divided by lambda. Lambda is what? 550. Now this 550 is in nanometer. We have to convert it into meters. Okay, so it is, or you write the 550 into 10 raised to minus 9. Okay, so after solving this, so which is the unknown quantity? N. So take it aside. This you transfer that side. So it is 10 raised to minus 17 into 550 into 10 raised to minus 19 divided by 6.626 into 10 raised to minus 34. Okay, into 3 into 10 raised to 28. So solve this and find out the number of photons. Yes, correct. It is 28. Correct. B. Okay. So this is the correct answer. Next, the energies E1 and E2 of two radiations are 25 electron volt and 50 electron volt respectively. The relation between their wavelengths, that is lambda 1 and lambda 2, will be. Okay. Now you know how, what is given, we have to find out the relationship. Okay, they have asked us the relationship between the energy and wavelength. Okay, energy and wavelength, the relationship is, it is inversely proportional. How you get to know? See, how is energy given? Energy is equals to h mu. Mu, how is the relationship between mu, lambda and velocity? It is c is equals to mu into lambda. So by substituting the value, you will see that E is equals to h c by lambda. So this is inversely proportional. So E is inversely proportional to lambda. So there are two energies now, E1 and lambda 1. So E1 and this is lambda 1. Then this is, you give it as 1. Then second, E2 is inversely proportional to lambda 2. Okay, this is second. Now from 1 and 2. So E1 by E2 is equals to, what will happen? This will go up, lambda 2. This is lambda 1. So now what are the radiations? This is given as 25 and 50 electron volt. Now electron, what is the charge of electron? Charge of electron is what? It is 1.609. Okay, electron 1.609 into 10 raised to minus 29. So now what you have to do is, now you write 61, even is what? 25. So 25 upon 50, okay, is equals to lambda 2 by lambda 1. So this is 1, 2. So just see, it is 2 lambda 2 equals to lambda 1. So from this we get the answer. What is our answer? Answer is C. So the relationship between their wavelengths is lambda 1 is 2 times lambda 2. Okay. So this is the correct answer. So next question, a wavelength 4 into 10 raised to minus 7 strikes a metal surface which has a work function 2.13 electron volt. The kinetic energy of emitted electron is, okay. So what all is given? Wavelength is given and the work function is given. Okay, we'll solve this. So solution. So from photoelectric effect we have, so what all we have? Lambda is given, lambda is equals to 4 into 10 raised to minus 7 meter. Okay, then what else is given? Work function is what? H mu naught, right? Work function is H mu naught, that is given as what? 2.13 electron volt. So this electron volt, it should be converted, means what? You have to multiply this by electron. So now kinetic energy we have to calculate. Kinetic energy is what? H mu, okay, H mu minus H mu naught. Okay, kinetic energy is equals to H mu minus H mu naught. Now kinetic energy is given as what? Kinetic energy of the emitted electron is, okay. So kinetic energy is to be found out. Now H is what? H is H mu by lambda. This you further simplify, that is H is equals to mu is C by lambda minus H mu naught. Okay, so HC by lambda, when you take this side, okay, what it happens? Kinetic energy is equals to H mu by H mu naught. So what happens here? You take H mu here and this becomes H mu naught plus kinetic energy. Okay, after this you have to add the, so just replace this now, h by c lambda, okay, is equals to work function is given as what? What is the work function? Work function is h mu naught plus kinetic energy. Now you substitute everything. So it is what? 6.626 into 10 raised to minus 34 into 3 into 10 raised to 8 divided by, what is the value of lambda? It is 4 into 10 raised to minus 7. Okay, is equals to, what is h again? H mu naught. H mu naught value is given. What is h mu naught value? It is work function. What is work function? It is 2.13. You have to multiply it by electron. That is 1.609 into 10 raised to minus 19. Okay, plus, just a second, plus kinetic energy. Now, from this equation, you solve and find out the kinetic energy. So this 6.62, okay, it will come to, when you multiply this first 6.626 into 3, it will come, and now this minus 34 plus 8, it will give you what value? Solve this. After solving, so at each step, you first solve each step and then go accordingly. Yes, what is the answer? After solving, what you are getting kinetic energy? So the kinetic energy will come to 1.5. Please solve this and see, okay? The kinetic energy comes to 1.5 D. Okay, correct. So today we'll stop it here and we'll continue the remaining part in the next class. Okay, thank you. Thank you, students.